you could solve that question? Well, okay, what we're going to do is we're going to do our diagram. So we're going to do our free body diagram, and we're going to say, what do you think our reactions are? What's our reactions on each side? Sorry?
28.
28 each?
Yeah.
Okay. And so we can draw 28. What's our shear force diagram going to look like?
1 up 48. 1 down 56.
So the shear force, our maximum shear force is 28 kilonewtons. That's the maximum we need to design for. Okay, then what does our bending moment diagram look like? To try like that? Okay, so what is the value? Okay, 28 times 5 is 140. I'll believe you. That sounds about right. Kilonewton meters. Right. Is there an easier way we could have done that? Could we have saved ourselves some ink? We could have said it's a simply supported beam, so we can say in this case, M max equals FL on 4. What is F?
56.
56 kilonewtons. What's L?
10.
10. A lot of people would get that wrong. Yeah? And then 4. Okay, so what we're going to get is we're going to get M equals 56 times 10 divided by 4, which is going to equal 560 divided by 4, which is
140.
kilonewton meters. Now, if you can draw that diagram quickly, hey, at least you'll be less likely to fall in the trap of not getting L right. Yeah, you'll show a little bit more more knowledge, but I like that method. It's up to you how you approach it. What we know now is we can say, for whichever method we're using, we know that M, or the M max, is equal to 140 kilonewton meters, which is the same as saying 140 times 10 to the 6 Newton millimeters. Are we okay with that?
Yeah.
There's 1,000 kilonewton is 1,000 newtons, and a meter is 1,000 millimeters. 1,000 times 1,000 is 1,000,000. Yeah, so that's where we get 10 to the 6. And you're okay with that? Okay, cool. Okay, what is the next thing we need to use? We need to have, so if we want to try and find this formula, right, sigma B, right, bending stress is equal to M times Y over I. What's the next thing we need to know?
Find
Y. Okay, so Y is, what value of Y are we going to use here? It is given to us. Can you tell me what value we're going to use? We have 100 and 200. Which one are we going to use?
Big one.
Big Y! Okay, so we're going to say Y equals 200 millimeters. Now, Copeland, I love Copeland's work, right? I think he wrote an excellent textbook. The one thing that irritates me is he always gives the answers in, he always gives Y, or I rather, in, he uses it in meters. Now, I'm not super smart. I'm going to say this in front of the camera. I'm not super smart, so if I get something that gives me the answer in meters to the power of 4, I would use everything in meters, which is exactly what Copeland does, right? He's going to convert everything to meters. So what he said is 140,000, well, we actually want the big answer, right? 140,000 times 0.2 meters times the I value, which he's given in meters, in 4.6 times 10 to the negative 4 meters to the power of 4. the thing is, no steel supplier will ever give you an I value in meters. They will always give it to you in millimeters to the power of 4. Very quickly, why is it millimeters to the power of 4? The answer is, so I'm not even going to write the answer, we're just going to look at Copeland's answers. We can choose this or this. Which one is the one we need to design for? The big stress or the little stress?
The big one.
The big one. Yeah, the big one is the one that's going to break the beam. So we need to worry about the big stress. Now, before I move on, I want to say, why is it millimeters to the power of 4? The idea is it's a second moment of area. We take an area, instead of it being a force times a distance, we take an area times a distance. So it's an area, which times a distance, and then we take the second moment of that. We take another distance. So area is millimeters to the power of 4 times millimeters gives us meters to the power of 4. Yeah. Or I like to use millimeters, which gives us millimeters to the power of 4. Yeah? That's why it's in this ridiculous concept of you can't actually have a millimeter to the power of 4. Yeah, you can have a cubic meter, but you can't have a millimeter to the power of 4. It's because it's not really it's not a physical dimension, right? It's a calculation, it's a property of the material. It's a property, not a property of the material, it's a property of the shape. Yeah, it's to do with the shape of the material. Also, it's important to know that if you have this amount of material, or you turn that same amount of material into a beam like this, the difference is that this one now has more depth. That's not unreasonable. Let's just move a little bit like that. Yeah, this one now has more depth. And because it has more depth, it's going to have a bigger I value. It's also going to have a bigger Y value, and that's going to bring it down. But because the I value is to the millimeters to the power of 4, right, it really increases. Yeah, strength goes up by, the bigger the distance. Let me show you two examples. If I wanted to build a beam, not a column, but a beam, and I could choose between one that was 100 millimeters or the same amount of material that was 50 times 200, I would always choose this one, right? Because this one is going to have a lot more strength for bending because it's got a big D, right? And big D is good. Okay. Okay, let's see if there's any more questions. Okay, so the next concept I really would prefer to talk over the screen rather than talk in front of the board. But the idea is there's something called a uniformly distributed load. And the idea is that all the points we've looked at so far have had a single 1-ton load right in the middle of the beam. But it's much better if you can to spread that 1-ton load instead to spread it out over the beam. And they give a different diagram. Now I'm going to go through some notes later where I'm going to talk about that concept. We're going to look at examples and we're going to go through that concept in a bit. But it will be a separate video to this one. But before I move on, in terms of the HSC, you are never required to calculate uniformly distributed loads. You're never required to calculate uniformly distributed loads. You are only required to be able to recognize and be able to identify, to match up. Say, which diagram matches this load case. You never have to do calculations. At uni, you'll almost always, and in practice, you'll almost always use uniformly distributed loads. It's very rare, it's rare that you use point loads. Like obviously a train going into the side of a building, inside of a bridge, that was something you designed for, that's always a point load, and it's usually a critically important part. But if you have a wall that's being supported somewhere along here, if you have a load-bearing wall, then you have a point load. But most of the design calculations will always involve some amount of uniformly distributed loads. So that's what UDL stands for. It's important. Okay. Before I move on too much, I will talk at least at this length, right? I'll say that in this case, what we're looking at is that if we said this is 10 newtons, kilonewtons per meter, and let's say it was 4 meters long. Well, if this was 4 meters long, this is going to be, how many newtons are there total? There's going to be 40, yeah? If there's 10 for every meter, and there's 4 meters, there's going to be 40. So that means the reaction is going to be 20 and 20, yeah? As we walk along, if we walk along half a meter, well, half a meter we're going to go down 5, right? So we're going to be at 15. We walk along another half a meter, we're now at 10. We walk along another half a meter, we're at 5. We walk another half a meter, we're now at 0. And now we're at -5, -10, -15, -20. Yeah, that makes sense? If we were taking the area of that slice, right? If we were taking the area of that slice and then comparing to the area of that slice, and at uni you will actually do this. You'll see that as you move along these slices, you'll see that the area there is obviously much less than the area there. So it goes up quickly, but then it starts slowing down. It goes up quickly, but then the area here is very small. The area here is probably twice as big. The area here is bigger again, and then here is where we have the biggest area. It gives us a curve. And let's have a look at when we combine these forces. Here, once upon a time, we had this beam, and I don't care enough to do the actual numbers. I'm going to say, well, if that's 10, this is probably 3, right? So once upon a time, we had this beam, and it went up 3. Then it went across some distance, and then went down 10. And went across again, nothing happened at this point. And then we had a big sudden reaction, a reaction of maybe 15 or something like that, 17. And then slowly it went down over the course of the, if that's 7, right, went across a meter, went down 5 kilonewtons, and then went down another 5 kilonewtons, down another 5 kilonewtons, until eventually it's at 0. Yeah? Now, what that looks like here is here, our bending moment diagram is going to be straight. Because this area is a square, that means this line is going to be straight. Because this area is a triangle, it means this is going to be curved. Does that make sense? Wherever we have triangles, we get curves. Wherever we have squares, we get straight lines. Yeah? That's pretty much how we match these up. I'm going to go through in a second. I have some examples. I have 4 that I do as a matching activity that I'll either set for homework or we'll go through in class. Okay, and from there, that's the end of bending from the Copeland book. Next thing we're going to do is we're going to go over stress and strain.